NASA has a plan to build a base on the moon before sending humans to Mars, to shorten the journey to Mars. SpaceX's founder Elon Musk wants to win the race to Mars. Additionally, European and Russian space agencies are also discussing sending humans to Mars. However, the main question is how humans will survive on Mars, especially since, unlike Earth, Mars lacks oxygen, which is vital for life. What method has NASA discovered to generate oxygen on Mars? And why won't the method used on the International Space Station work on Mars? There are many reasons behind the desire to live on Mars, including scientific exploration and space curiosity. But there is also a fear or necessity. This is due to the fear of a catastrophe on Earth that could end human existence, similar to the extinction of dinosaurs 65 million years ago. This seems possible, as seen with climate change on Earth. Perhaps this is the biggest reason why there will eventually be a Neil Armstrong of Mars. Elon Musk initially planned to colonize Mars by 2026, but has now predicted 2029, while NASA also intends to land humans on Mars by 2030. But the question isn't just about who will get to Mars first, it's about how humans will survive there. Mars has many properties similar to Earth, such as the length of a Martian day, Sol, being only 39 minutes longer than an Earth day, and having various seasons and ice caps at the poles, as well as an atmosphere, albeit thin. However, the lack of oxygen on Mars is a significant challenge for human habitation. Therefore, a system must be developed that can generate oxygen on Mars using local resources. The International Space Station, ISS, has survived in harsh space conditions for 25 years, continuously providing astronauts with oxygen and fresh water. The ISS usually hosts 5 astronauts who require at least 45 liters of water daily, equating to about 1,350 liters per month and 16,200 liters per year. Additionally, the ISS uses about 1,000 kilograms of oxygen annually. How are such large amounts of water and oxygen produced in space? 400 kilometers above Earth. The ISS uses 2 systems for this purpose: the Water Reclamation System, WRS, and the Oxygen Generation System, OGS. To understand why these systems cannot be directly applied to Mars, we must first understand how they work. The WRS recycles human waste, such as urine, sweat, and humidity, purifying it for reuse. Astronaut Douglas Wheelock once said, "Yesterday's coffee becomes today's coffee." This system helps to recycle 98% of the water on the ISS. The OGS, on the other hand, uses a small amount of water from the WRS and splits it into oxygen for breathing through a process called electrolysis, familiar to many from 5th grade science. Electrolysis involves passing an electrical current through water, separating it into oxygen and hydrogen gases. The oxygen is used for breathing, while hydrogen, a highly flammable and dangerous gas, is not wasted but utilized in another system called the Sabatier system. This system combines astronauts' waste, CO2, with hydrogen to produce water, methane, and a bit of heat. The water is recycled, the heat is used in the heat management system, and the methane, though valuable on Earth as a fuel, is released into space on the ISS due to the premium value of oxygen. The ISS's oxygen and water systems depend on refueling missions. Although 98% efficient, these systems experience losses and leaks, requiring periodic refueling from Earth, a costly endeavor where even transporting a liter of water to the ISS can cost over $2,500. Hence, replicating this method on Mars, 225 million kilometers away, is not cost-effective. A system must be devised that uses resources available on Mars to generate oxygen. The 2021 NASA Perseverance rover mission included an experiment for this purpose: the Mars Oxygen InSitu Experiment, MOXIE. Unlike the ISS, which relies on refueling for its water source, obtaining water on Mars would require accessing its polar ice caps or drilling deep for ice. Therefore, MOXIE generates oxygen directly from Mars's atmosphere, which is 95% CO2. MOXIE pumps CO2 from the Martian atmosphere, pressurizes it, and then heats it in an electrolyzer at 800 degrees Celsius to separate oxygen gas. This electrolyzer is made of gold, a great heat conductor, protecting other parts of Perseverance from excess heat. The process also produces carbon monoxide, which could potentially form a damaging carbon layer, similar to what is seen on cooking pans. Thus, the process is performed with great caution. However, MOXIE currently produces only a limited amount of oxygen, about 122 grams, enough to sustain a person for just 3.5 hours. To produce more oxygen, a larger version of MOXIE and a substantial power plant would be required, which is currently a significant challenge. Future technologies are being developed to split CO2 molecules at lower temperatures, potentially using vibrations to separate oxygen molecules, a method that has been tested in labs but is impractical on Earth due to high atmospheric pressure and temperature. However, Mars's atmosphere is ideal for this approach. Ultimately, the goal is to use a system on Mars that relies solely on local resources to generate oxygen, reducing dependency on Earth. This is crucial, as the ISS is only 400 kilometers from Earth, making emergency returns feasible. In contrast, resolving any oxygen generation issues on a colonized Mars would be far more challenging, as refueling and returning to Earth would not be easy options.